sorry, I was just checking all my settings there. Hey, this is section 6.1, area between two curves. I know that we went over a couple examples, but here are all of them together. So far, we've been finding the area between the x-axis and the graph of a function. Suppose both boundaries are graphs of functions. We still divide the region into rectangular subintervals or partitions. Mrs. Charnley uses stick figures. Each one has the width of delta x, which we did with our rectangles, but the height is the function on the top minus the function on the bottom. We will still use the definite integral from a to b to add together all of the rectangles. And then this is the, let me change the size of this. This is the integral formula that we'll be using. It's really, really not too bad. So example 1, find the area of the region enclosed by the graphs of y equals 2 minus x squared and the line y equals negative x. So 2 minus x squared is a parabola, goes up to 2, and it points down because x squared is negative. The line y equals negative x is a line that has a y-intercept of 0 and a slope of negative 1. I missed my dots there a little bit, but pretend they go through. And then the area that you're finding is this area in between the two curves. So no longer are we stuck on the x-axis. So the way that you set this up, it's a definite integral. You take the function that's on the top, which is 2 minus x squared, minus the function that's on the bottom, oops, which in this case is negative x. And this is a dx problem because the partitions go up and down. So up and down, up and down. I like a little stick figure to remind me that the head is at the top and the feet are at the bottom. You won't see that in a textbook. You might see it on a YouTube video somewhere, but that's kind of my thing that I've relied on as I've been teaching these. Now, this is a dx problem, which means my partitions are vertical. dy is a thing, but we're not going to touch on that this year. The other thing we need is our a and our b. And those occur when the two lines intersect each other. So you want to set them equal to each other. I'll say negative x is equal to 2 minus x squared. Now, I've seen some crazy trying to solve when there's an x squared and an x in there. We know that algebra 1 and pre-calculus were a little bit bumpy. So let's move everything to the left-hand side. You want this equal to 0. So x squared minus x minus 2 is equal to 0. And now you're going to factor. So this becomes x minus 2, x plus 1 equals 0, which gives me x equals negative 1 and x equals 2. Well, what are those? It's where the two graphs intersect, negative 1 and 2, and then they become our boundaries. So this is negative 1, this is 2. Now, you can reorder things. You can simplify your negative signs inside a little bit to make it nicer and neater. Maybe if you want to write it in standard form. You are all capable of calculating this by hand with the fundamental theorem of calculus, but I'm not asking you to. So if we're not, we're going to hop into Math 9. Now, I think I already calculated this one. Yes, I did. Here's what it looks like. No, this one. There we go. And when I hit enter, I have 4.5. So my area between the two curves is 4.5. So with all the work that we've been doing with area before, these are actually a nice extension of that. They're not too crazy. Example 2, find the area of the region enclosed by those graphs. So we have y equals the square root of x You can put that in your calculator to see, or remember it looks like that. And y equals x minus 2. So down to up 1, right 1. And then we also have the y-axis. And the y-axis is this one. And the equation of the y-axis, I know it feels weird, is x equals 0. So the equation of the y-axis is x equals 0. The equation of the x-axis is y equals 0. I know it's a little funky. And then the area that we're looking to find is this area over here. So when we set up our integral, we'll come back to the boundaries later. Again, what's on top, what's on bottom? The square root of x is on the top, minus x minus 2 is on the bottom. And then this is a dx problem. Now, my boundaries are where they intersect. So A is over here, and then B is this point. So they intersect at the y-axis, well, they don't actually intersect. They start at the y-axis, which is x equals 0. And then they do intersect over here, wherever that is. So I'm going to set them equal to each other. I'll say the square root of x is equal to x minus 2. Again, I've seen some crazy algebra solving here because algebra 2 and pre-calc were a little bumpy. You'll all tell me that's x. Some of you on the right-hand side are going to try to tell me it's x squared minus 4, but it's not. You really have 2 of them. So this is x equals x squared minus 4x plus 4. And again, you want this whole thing equal to 0 so that you can factor it. So 0 is equal to x minus 1, x minus 4. So x is equal to 1 and 4. Now, which one do you use? You're actually going to use the 4 because that's the one on the right. They intersect over here when x equals 4. Now, where this 1 comes from, or where do I see it? I don't see it on the graph. Well, if you have y equals the square root of x and square both sides, y squared is equal to x. Y squared is the parabola that lies on its side. So we have part of that already, but then the other part would come down here. So by the calculations, it looks like that they intersect right here when x equals 1. It's a domain question, and a range question. We're not going to get into that, but just know that we don't need the 1 for this problem. All right, math 9. Again, I'm going to cheat because I think I already did that. Square root of x minus x minus 2, I did. And when I hit enter, I have 5.3 repeating. I know those last decimals get a little crazy. It's just how the algorithms work. It really is 5.3 repeating or 5 and 1/3. My area is 5.3. Awesome. On to the next, example 3. I think I have 3 examples on this page. Yes. Find the region, find the area of the region enclosed by y equals x squared and y equals x. So y equals x squared is a parabola. Y equals x is a line with a slope of 1 that passes through the origin. So it's a little tough to see on here, but this itty bitty sliver of area, I'll try to make it bright. This is what we're calculating. And my thick pen line makes it a little tough to see, but that's what we're calculating. So when we set up the integral, I'm just going to set the whole thing up in gray. We'll come back to the boundaries. The one on top is the line. The function on the bottom is x squared, and this is a dx problem. Top minus bottom. My boundaries, I can set them equal to each other. X squared equals x. So x squared minus x equals 0. Factor out an x, x minus 1. X is equal to 0 and 1. You can put that in your calculator. This one I don't think I have yet. All right, put that in my calculator. This one's really small. 0.16 repeating. And that 7 just comes up because when they round it at the end of the screen, the next digit is 6, which becomes 7. All right, example 4, my iPad's or my laptop's about to die here. We'll see what we can do. X squared minus 2 and y equals x. I'm just going to use the same pen color to speed this up a little bit. X squared minus 2 is a parabola. Y equals 2 is this horizontal line. Here's our shaded area. Our integral would be, we'll come back to the boundaries. The top is at 2. The bottom is at x squared minus 2. It's a dx problem. When I set the two pieces equal to each other, 2 equals x squared minus 2. 4 equals x squared. X is plus or minus 2. You could factor that as well, but you don't have to. So there's my integral. This is my side work. My area is equal to -2. There's a lot of 2's in this problem. Don't forget parentheses on the second piece. Otherwise, you will have sign errors and it will be a mess. So as long as your parentheses, you have a pair, everybody has a buddy. You can't have too many parentheses. This one is 10.6 repeating, which is really 10 2/3. Now, again, you could solve these by hand, entirely possible. I'm just not asking you to do that right now. All right. And look at this. I'm so quick to copy and paste. This one's really example 5, not example 4. Find the area, sine of x and y equals 0. So y equals 0 is this line. Sine of x, 3.14 would be pi, which is right there. You get one wave, 1/2 of a wavelength between 0 and pi. So the area that we're attempting to calculate is this one. Now, the nice thing about this integral is they already told us what the boundaries were. They are 0 and pi, sine of x dx. You could do that by your hand. The antiderivative of sine is negative cosine. Between 0 and pi, so negative cosine of pi minus a negative cosine of 0. Cosine of pi is -1. Plus cosine of 0 is +1. So we have 1 plus 1, which is 2. If you use your calculator, if you use Math 9, use radians. Math 9, radians, because anytime you hit that sine, cosine, or tangent button, our problems in calculus are set to work with radians, which give you much smaller numbers. If you're in degrees, things get very, very big, very, very fast. There you go, my friends, area between two curves. I want you to try these 10 problems. I had the worksheet print out with the graphs already, so you don't have to stress out about that. Some of these already have A and B given to you, the boundaries. I know they call them X and X, but this would be A, this would be B. This would be A, this would be B. Actually, I think they all have them. The first one is your A, the second one is your B. So you don't have to set them equal to each other. Like I said, I want this to be a good introduction. I know we're short on time. I don't want you to stress out about these. So do your best, give them a go, and you can check your answers in Schoology. All right, thanks.